Today's lesson is over section 5.2, the definite integral. So here for our warm-up problem, we're supposed to approximate the area under y equals the square root of x plus 1 from 0 to 2 with 4 rectangles. So using the left endpoints, and we want to kind of decide whether that's an underestimate or an overestimate. So first thing we need to do is to identify what the change of our x is, so the width of our rectangles. So that would be from 2 to 0 divided by how many rectangles we have, which is 1/2. And then 1/2 times all the heights from the left endpoints touching our curve for square root of x plus 1. So that gets me 1 plus the square root of 1.5 plus the square root of 2 plus the square root of 2.5. So adding all those together gets me approximately 5.2200 something. And then 1/2 of that gets me 2.61. And because you have those little gaps there must be an underestimate. Okay, so today we're going to be talking a little bit about summation notation with our definite integrals. So you have all the notation there. So summation notation, that little e thing just means you're adding all the values up. N is the last number you're adding, I is the first number, and so that many terms is what you're putting together. So there's a function in there. And so with the formulas here, you can do this from a number all the way to a number n. And so there's different notation formulas that you can see at the top, A through E. And so we can find the area underneath a curve by taking the limit of all those values put together. So let's practice a couple here. So first we want to kind of split them all up into their own separate notations. So I squared and then 3i and then 4. If there's any constants, you can move them out front to make your substitution easier, but it's also not required to do so because it's just multiplication of whatever formula that you're using. So here, I squared should be n times n plus 1 times 2n plus 1 all over 6. And then the next one, I, should be n times n plus 1 all over 2. And then 4, since it's just a constant, it'll be 4 times n. And so from there, we want to be able to simplify. And so I'll multiply my parentheses out on both of these fractions here. And then I'll multiply my n or my 3 through and make common denominators so that I can actually put all my like terms together, because the most common denominator is 6. And so then from there, I'm going to simplify a little bit by putting like terms together. And then if there's any factors on the top and the bottom I can reduce, I will do that. That gets me n cubed plus 6n squared plus 17n all over 3. And I'll do the same thing for letter B. Here, first you have to distribute that I through and get rid of the parentheses. And so I don't have to split them up into their own thing. I can just plug them in as is. So 4 times the I cubes formula, which is n times n plus 1 all over 2 squared. And then I is n times n plus 1 all over 2. Then I multiply those out so that I can put like terms together. So now once I've multiplied and put all my like terms together, I can simplify to get n to the 4th plus 2n cubed minus 1/2 n squared minus 3/2 n. So where this applies is we can start putting it to an actual function with an actual graph. So here I have a function that is negative x squared plus 16. I want to divide this up into 25 sub-intervals of equal length. So I need to decide what my width is based on that number of rectangles, and then from the interval of 0 to 2. So I'm going to start with the first rectangle. So the counting is I'm counting the areas of all the rectangles from the first one all the way to the 25th. And so just like we did with the other one for the warm-up, we have the change of x, which is 2 minus 0, divided by how many rectangles I have, which is the width of each rectangle of 2/25. And so because we're counting, I is actually indicating which rectangle you're on. And so I want to find the height of these rectangles, and so that I can multiply it to the width, and so then I can get all their area. So 2/25 gets me my width, but gets me to the proper location as well, times the I value, which gets me to the proper rectangle, so I can actually find that. So those are all approximations. So how do we actually get the right value rather than an approximation? Well, that's where definite integral comes in. So from the integral from a to b for the function of f of x dx, it is the same as doing the limit from n to infinity of that summation notation that we kind of just set up in the last example. So notice that Riemann sums leave a gap, definite integrals do not. One thing to keep in mind is that we can have negative area. So when your curve goes below the x-axis, you are able to get a negative value. So area 1 subtracted to area 2 plus area 3 would be that area, something to keep in mind down the road. So here we want to find the definite integral of the function x squared from 0 to 2. So we need to find that width. Now because they're not telling us how many intervals or rectangles we're going to use, we're going to say it's n, which means that we can do it to infinity because we're approaching infinity. So that is our width that we plug in. And now our width times our I gets us what we're plugging into our actual function. So 2 over n times I is what I'll plug into my function of x squared. So then notice that I attached a square there. Now I can also move the 2 over n, which is just a constant in this case, out to the front of the sigma notation like we practiced on the last example. But I can't move it all the way out in front of the limit because I'll need it. So now I can multiply that square through, move the 4 over n squared out with the 2 over n to make it 8 over n cubed, which allows me to just isolate the I squared so I can insert the formula that we were practicing in example 2 so that we can actually simplify this the same way we did with this example 2 problems. Now once I've done that, I can reduce my fractions, and so then they're simplified. And so once I have that, one of our limit properties is that if you have anything over n or a variable and that variable is approaching infinity, that value is basically 0. So for 4 over n and 4 over 3n squared, those values are 0, so that allows me to do 8/3 plus 0, which is 8/3. So my actual area under the curve for x squared from 0 to 2 is 8/3. So I can actually find an exact value now. So letter B, same thing, but here notice that we're not starting at 0 anymore, we're starting at 2. So we have to incorporate that into our calculations. So it is going to be the change of x times I plus what our starting value is. We didn't do this before because the starting value is 0, and so that doesn't change the change of x times I. So now I'll have to do 2 over n times I plus 2 because I'm starting at 2. 2 over n is still my width, and I can still move that out front. I will have to plug in 2 over ni plus 2 into my function of 2x minus 1, and then simplify. Here I won't be able to move everything out like I did previously because I'll have two terms that have separate values attached to them. And so I'll have to leave it as 4 over n times I plus 3. And then I can, from there, plug in my summation notation formulas. So 4 over n is my constant times i's formula, plus 3 times n, which is a constant's formula. And then I'll do the same thing. So now once I've separated them all out, I can simplify my fractions. And so that allows me to get 4 plus 4 over n plus 6. And so 4 over n, when I plug in infinity, gets me the value of 0. So 4 plus 0 plus 6 gets me the area of 10. Okay? Thanks. Have fun.